Ever wonder how a robot could figure out teamwork on its own? Or how a group of digital creatures could learn to communicate without being told how? Let's explore a mind-bending study about these tiny AI pioneers, called Animats, and how they're rewriting the rules of machine learning. Imagine a world where these digital creatures are on a mission, building towers, dodging enemies, and figuring out how to work together. But here's the twist: they don't start with a manual. They learn by doing, making mistakes, and adapting. It's like teaching a toddler to ride a bike. They wobble, fall, and eventually find their balance. At the heart of their learning, two types of brain-like systems: an artificial neural network ANN and a spiking neural network SNN. Think of the ANN as the robot's logic board, processing info and making decisions. The SNN, that's its communication system, sending signals like a digital nervous system. But here's the cool part: they don't work alone. They share a secret tool: memory registers. These registers are like a shared notebook. Both networks jot down notes in 10 floating-point values, 5 from the ANN, 5 from the SNN. But here's the kicker: the meaning of those numbers isn't fixed. It's like a conversation, where the same word can mean different things to different people. Over time, the networks learn to talk through these numbers, even if they don't fully understand each other. Now, how do they make decisions? Every few seconds, they go through a cycle. 1. Sense: they gather info from their environment, like spotting a brick or sensing a rival. 2. Decide: the networks process this data, picking actions or signals based on probabilities. 3. Learn: they review their choices, tweaking their networks to get better. 4. Act: they execute the action, then repeat the cycle. It's like a robot's version of trial and error, but with a twist. The memory registers help them remember what worked and what didn't. But here's where it gets wild. These animats don't just learn individually. They're part of a larger system where entire tribes evolve together. Every 200,000 seconds, the tribe turns over, but the magic happens in between. It's like a relay race. New members keep the knowledge alive, creating a continuous flow of data. And when researchers tested different social structures, like hierarchies where older animats teach younger ones, something surprising happened. Tribes with age-based hierarchies outperformed others. Why? Because experience mattered. Older animats, having learned from past mistakes, could guide the young, blending raw talent with wisdom. It's like a mentorship program for robots. So what does this all mean? These animats aren't just stacking bricks. They're building a language, a strategy, and a way to adapt. It's a tiny glimpse into how communication shapes survival, whether in robots or real life. But here's where the real innovation lies. These animats don't just learn, they improve their own learning. A 1996 study showed that by letting AI agents tweak their own algorithms, they could adapt to new challenges without human help. It's like teaching a student to solve puzzles, then letting them invent new puzzles to keep pushing their limits. Imagine an animat spotting a brick. It doesn't just grab it on instinct. Instead, it's like a tiny brain running a quick checklist. Should I wait? Chase it? Conserve energy? This is called state management. Think of it as the animat's mood swing. If it's in wait mode, it's lazy, conserving energy. If it's attacking, it's all action. And if it's fetching a brick, it's laser-focused, but only if it's not already carrying something. It's a balancing act, much like a bee deciding whether to gather nectar or guard the hive. Researchers track how different the animats' strategies are using something called the signal differentiation factor, basically a diversity score for behavior. If all the animats are doing the same thing, the score is low. But if they're experimenting with new tactics, the score spikes. This tells scientists if the group is flexible or stuck in a rut, like watching a sports team adjust its playstyle mid-game. And if things go wrong, no problem. If an animat fails or strays too far from the action, the system replaces it, keeping the simulation alive. It's like a GPS for digital life, snapping the animat back into the experiment if it veers off course. So what does this mean? It's a glimpse into how intelligence, whether in robots or real life, can evolve through trial, error, and a little bit of digital creativity. These animats aren't just mimicking life, they're rewriting the rules of what it means to learn. Stay tuned as we explore how this shapes the future of AI.